So, okay. So let's see. Will workshop assignments remain the same format? Yes. And can we rewatch the conference at a later time? Yes, you actually can. In fact, right before you said that, I just remembered I had to turn the recording on. So you won't be able to watch my little welcome, but you will be able to watch everything else that happens in this conference. About half an hour after we conclude the conference, there will be a link on Canvas in the same place you joined the conference where you can see the recorded conference. It takes them like half an hour to process it, but then it shows up. Then I have 2 weeks at that point. It'll disappear from Canvas in 2 weeks, but I have 2 weeks to download it. I'm going to create a YouTube channel where it'll sit more permanently. YouTube also auto captions it. So if there's something you can't hear, you'll be able to turn the captions on and see it. So, we have, sort of multiple backups as to how, how you're going to be able to participate. Question about quizzes. So there are going to be quizzes this week. It's not going to be associated with recitation this week. There will be a quiz a little bit later in the week. I'll make it just to avoid, giving people extra stuff to do on non-class days. I'll make it associated with the next lecture day this time. In the future, what you'll normally do is you'll sort of break workshop 10 minutes early, and you'll take a quiz on sapling. Because we have people all over the world, we have people, people participating from many different countries, some of which are in quite distant time zones. We can't exactly insist that everybody take a quiz at the exact 10 minutes at the end of workshop. So what would happen is sapling, I will set it up this way. So it'll give you like a 24-hour window to open a quiz, at which point you'd have whatever time I allot for it, like 10, 15 minutes to do a problem. It'll basically look like a homework problem. The only difference is you won't get more than one attempt on it, and it will count as a quiz grade. So that's, so you can't get partial credit now. Well, so you can, in the sense that there will be several questions and you can get some of them right. Planning to get every question wrong was never a good strategy in the first place. So perhaps that's a good thing. Let's see, what are the next questions? Oh, somebody asked, when will receive your derivative quiz scores back? I have them. They've been entered into the Akindi program. I just have some sorting and processing to do. Obviously, we've been a little busy this week getting this ready up, getting this online format ready. So just be patient. We'll take care of that. So let's see. Let's see. All right. I think that some of these questions that are showing up are of more specific interest to people. That's a good question, but I'm going to move on after this last question. The question is, will we be able to take the sapling quiz at any time of day? And the answer is yes. I will set a 24-hour window, after workshops, during, or in this case, after lecture, during which you can take it. So you don't get 24 hours, but you can choose which time in the 24 hours you start the quiz. So, okay, let's see. All right, so the next thing is, it occurred to me that, as I really enjoy actually being in class, and I was trying to think sort of how we can humanize this, format. That seemed to me to be a fairly important thing to keep everybody involved. So I came up with a couple of different ideas. The first one was just download some sort of laugh track so that it could be like a TV show, and it would be just like regular class. I say something funny, you guys laugh. I decided that perhaps did not strike the right tone. So one of the things I did early during break, I was still trying to process all the stuff that's going on, is there are actually many there are many parks near my house, and those of you, if any of you live in the Princeton area, you might even know of some of them. The so they one of my favorites has a thing called the Scott and Helen McVeigh Poetry Trail. Some of you, again, if you're from Mercer County, you might have seen this at it's at Greenway Meadows Park. So what I realized, I've gone there before, and I realized that some of the poems are just sort of simple odes to nature, like Ode to a Butterfly or something like that. But a very large number of them are about time and perspective. So I thought that perhaps every day I could introduce, assuming I remember to do this, as I'm not always good at remembering that. But as long as I remember to do this, I could introduce something from one of my various walks in the park, which is now the only thing, of course, that you're allowed to do for recreation. So, I photographed some of the poems from the park, and there's also another park that's actually perhaps even more interesting in some ways. It's a memorial to the international telephone technology that was used about 100 years ago. So it's got historical exhibits on how on a place called the Pole Farm, about how phone calls were placed internationally. It's quite interesting, actually. So maybe we'll do that someday. But for today, let me put up the screen sharing. And give me just a second. Let's see if this screen sharing works, or if everybody going to online, there we go. Everybody going to online classes has blown up the system. So today's poem from Greenway Meadows Park, from the Scott and Helen McVeigh Poetry Trail, is An Owl Dream. It says, in my dream, an owl beats spread wings against my window, promising a share of her kill. Small bones lodge in my throat, blood and sinews stain my tongue. Her wings move faster now, a white blizzard against the glass. Her eyes glare over a harsh beak. She wants my fingers, little animals that squirm on their own in the dark of my sleep. She wants to tell me it's all right. We can both have everything we need from the same field. There we go. So that's today's poem on perspective. We will now start the math part of the course. Okay. Okay. By the way, I hope I'm demonstrating this now with the mouse, but as you see, there's the usual icon that allows you to make what you're seeing full screen. So you might find it easier to read what we're doing if you click that. In fact, since I'm just going to be talking, and as much as I know you guys like to see me here behind. That's interesting. I was going to say the spare bedroom with all the junk in it, but actually, when I told my wife I was going to be using this room, I think she cleaned up all the junk. I think she was actually embarrassed to have everyone see it. So I didn't notice that till now. Anyway, I'm going to turn off my video for now, and I'll just talk. So, because I think that'll give you more access to the screen anyway. So, yes, Leah, I will thank her. There we go. Okay. So, and by the way, if there's time, I will try to circle back to another linear approximation example, because I know we went through that kind of quickly, but I want to get through to the next topic. Okay, so we're now into we're going on to section 4.2. I'm just looking at I have two screens set up. I'm just looking to see how well you can see this. So I think this is working pretty well. I'm sorry, someone said unhide presentation. Can you all see what I'm writing? Can you see that I wrote a 4.2? Okay, good. Okay, so what we do is we define we suppose the function f is defined on an interval I, and if you let a be any number in the interval, the question is what is an absolute min, an absolute max, and an absolute min. So basically, f of a, which keep in mind is a y value of the function, is an absolute max, an absolute maximum if it's greater than all other values of the function on that interval. So we can draw this. So I have, let's say, a, and that's b. So here we have I is equal to the interval ab. So what we say is that, see, there's f of a, f of b, and here's the lowest value. So here we have the minimum value, and here we have the maximum value. So it's not that the function doesn't attain higher values somewhere else. It's that on the interval AB, these are in fact the lowest and highest y values that the function attains. If you notice, it attains its highest value at one of the endpoints, and it attains its lowest value at some interior point in the interval. So there's no guarantee that it's good that the maximum value is going to be either at the endpoint or not at the endpoint. We'll see shortly how we determine when that's going to happen, but this is just the definition. So basically, these definitions mean more or less what you think they do. Maximum value is going to be the highest y value of the function. Minimum value is going to be the lowest y value of the function. So the next point is just a little terminology, and a lot of what we're going to be talking about for the next couple of slides is terminology. We say that f of a is an extreme value if it's either a minimum or a maximum. Often, because math uses a lot of Latin, you'll hear the term extremum. So I'll often refer to an extreme value as an extremum. The plural is extrema. Some people say extrema. So what we'd say here is that these two values that I've shown, f of a and f of c, are the extrema of the function f on the interval ab. So and also we have similar terms for minimum and maximum. So the plurals, the function could have, we'll see in a minute why there could be more than one minimum or more than one maximum, but when you use the plurals, we refer to minima and maxima. Okay. So this is just a definitional matter. This is just defining precisely what it means. What it means to say that a value is an absolute min or an absolute max. One thing I want to point out is, oops, there we go. F of a is the absolute max, not a. In other words, people often will say, oh, A is the absolute maximum. No, A is the place where the maximum occurs. The absolute maximum value is a Y value. So, okay. Let's see. All right. So any questions about this definition? I get the feeling, just I can't actually hear this being an issue, but I just get the feeling from some things people are saying that there's actually audible chatter. I've tried to actually mute everybody, but I would just out of courtesy, since there are looks like 77 people in the conference, just appreciate if you'd mute your microphone if that's an issue. Okay, good. I thought trying to read the chat and see what people could hear. I have a little bit of a different view of everything than you do. Okay. Okay. So next definition is the notion of a local extrema, or local mins and maxes. So a local maximum, we said that f of c is a local maximum, or sometimes you see the term relative maximum, if f of c is the maximum value of f in some open interval that contains c. And similarly for local minimum, that would be a local or relative minimum if f of c is the minimum value. So before I draw the picture, just try to understand what this actually means. The idea is that it may not be the case that f of c is the highest value of the function, but it could be the highest value around for some distance in either direction. The way you can think of it is if you're standing on top of a mountain, you're clearly on top of the mountain. You're the highest point around you. Doesn't mean there isn't a taller mountain someplace else. Just means that right now you're at the highest point that you can see. So the picture basically looks like this. So looking at these two red points, this is a local max f, and this is a local min f. And you can see that clearly they are clearly these are the highest and lowest points around. So even though there are higher points and there are lower points, like this is lower, and draw this a little bit up. This is higher. So it's not that they're actually the highest and lowest points that occur anywhere on the function, but they're the highest and lowest points in what we call a neighborhood, or for now, I'll just use the term open interval. So the idea is if this is C1, notice that it is in fact lowest point in interval. And it's the same thing here. If this is C2, I can draw an open interval around C2, and that the red point above that is clearly the highest point. It is clearly the highest point in that interval. So, okay, so all right, so that's what the concept is. We'll see again shortly why this is relevant. Let's see. All right. Any other questions about this this concept? Okay. Let's see. Okay. So now I get to a result called the extreme value theorem. As you all know, we have a lot of theorems in calculus that end with the phrase value theorem. We've seen the intermediate value theorem. So this is the next of our value theorems, and possibly at the end of today or earlier on the next lecture, we'll encounter a third value theorem. So the extreme value theorem says that both extrema exist for a function that's continuous on a closed and bounded interval, or stated more formally, you can see how I've written it here. If f is continuous on a closed and bounded interval, bounded just means that it's bounded just means that it has a lowest and a highest point, which in this case are a and b. Many people don't realize that the interval negative infinity to infinity is closed but not bounded. So that's why I say bounded here. For the most part, what you've been thinking of as a closed interval, you can just treat as a closed and bounded interval, because it gets in the question of why negative infinity to infinity is a closed interval, gets into the subject of topology, which we don't really want to do. So anyway, so if f is continuous on a closed and bounded interval AB, then f takes on both an absolute minimum value and an absolute maximum value on AB. So, all right, so let's see, what's the picture here? If this is AB, this is a function y equals f of x, and it's defined on the closed and bounded interval AB. Here, this is the absolute max, and this is the absolute min. So you can see the function actually does attain an absolute max or an absolute min. In this case, once again, they occurred at 2 points that were in the interior of the interval that I'm going to call C1 and C2. And also possible that they occur, say, this is A, B. No. It's also possible they occur at the endpoints of the interval, or it's possible that one of them occurs at an endpoint and one of them occurs somewhere in the interior. The point of the theorem is that as long as the function is actually continuous on a closed and bounded interval, these mins and maxes will in fact occur. A little bit later, I'll show you the counterexamples of why it is that you need these conditions, that the interval be closed and that the function be continuous on the interval. So let's see. Sorry, there was a question I just want to answer. Eric is asking, does an extreme indicate where an asymptote is? The answer actually is no. Just hold on for the slide that's coming up a little bit from now, and you'll see that I do have an example with an asymptote, and you'll see why that's not a minimum. The short answer is it's tempting to think of an asymptote as a minimum, except that in many cases, not all, remember, in many cases, the function actually never gets to the asymptote. So it can't be the minimum value of the function because the function never has that value. The function has to actually attain the value. If you notice here, how does the pointing feature work? There we go. I can sort of point. The function actually attains that maximum value, and you can't always say that about an asymptote. Some functions do cross their asymptotes, some don't. Okay. So, all right. Let me just ask if anybody has any questions about this particular fact. Okay. Let's see. Okay, so next topic. I know I'm throwing a lot of definitions at you, but you're going to see in a few minutes how this all comes together. So next concept is something called a critical number. Our book calls them critical points. I'll show you in a minute why I prefer the term critical number to distinguish why I prefer the term critical number, at least for single variable calculus, to distinguish it from the point itself. But basically, here's the definition. A number C in the domain of F is called a critical number or critical point if either f prime of C equals 0 or f prime of C does not exist. So, okay, what's the picture here? I draw If I draw a function like this is y equals f of x, then call that C1, we'll call that C2. So we say that C1 and C2 are critical numbers of f. And you can see why based on the definition. Here, f prime of C1 is equal to 0. How do we know that? Well, if you look at where the tangent line is, the tangent line is horizontal, and we've seen in the past that when the tangent line is horizontal, that means the derivative is 0. In fact, that was how we found horizontal tangents in certain problems in earlier sections. Here, we've also seen that at a place where the function has a corner, the function doesn't have derivative. So here, f prime of C2 does not exist. So recall a reason for this is that depending on which side you're approach, remember we call the derivative is a limit. So depending on which side you're approaching that point from, you would conclude here that the slope is positive, and here you would conclude that the slope is negative. And since you can't decide which one, what we have is two-sided limits that are not equal to each other. So we'd say that the derivative doesn't exist because you get different values on the different sides. We've sort of moved past that, and you can simply remember that if a graph has a corner in it, that's one of the reasons the derivative doesn't exist. There are some slightly different reasons also why it might not exist. Okay. So let's see. So there's one example of a function that has critical numbers. The reason, by the way, that I prefer the term critical number is that this is C1 is the critical number. This point here is actually C1 comma f of C1. That's the point, and that's why I'm not crazy about the book's terminology of calling the critical number a critical point, but I won't fault you for using either terminology. It's just that in general, what I'm asking you to do is find the actual number, the number along the x-axis where the function has a critical number, not the full point itself. So I'll just give you another example of. I want to give you another example of a function that has critical number. So clearly C1 is a critical number in the second function. We'll call this y equals g of x. So clearly C1 is critical number of g. Question is, what about C2? Actually, this is a place where you can participate. So let me ask you, what do you think? Is C2 a critical number or not? Oh, this is great. I can get more people to answer my questions than in real life. So, okay. So we got a little disagreement, but it looks like most people are saying yes. Okay. So It turns out that yes, C2 is critical. Now, why is C2 critical number? The answer is that here we have, of course, f of c. It's not it's f of c1, right? Not f prime of c1 equals 0. That's clear. But here we have is f prime of c2 does not exist. And the reason for that is, recall, f is not differentiable at points where not continuous. Okay. So that's a condition. You can't have a function, you can't have a derivative if the function is not continuous at that point. So here, that would in fact be the C2 is still a critical number. Okay. Okay. So go back up here. Here's what you really have to know about critical numbers is that they're defined simply as places where the derivative is 0 or they don't exist. All right, so now hopefully this is going to start to come together in the next slide. What do all these things have to do with each other? The answer is something called Fermat's theorem on the location of extrema. And what it says is that if f of c is a local min or a local max, then c is a critical number of f. What does this mean? It means that local mins and maxes can only occur at critical numbers. Therefore, we can find all the local mins and maxes by looking only at the critical numbers of f. Let's see. Oh, I'm getting a question. I'm sorry. Jules is asking, does continuity not matter? What do you mean by that? I'm sorry. Just clarify that. So, shouldn't the function be continuous in order for there to be a critical number? The answer is no, because go back to the definition. Critical number is defined as any place where f prime is 0 or f prime does not exist. So since a function can't be differentiable if it's not continuous, then that means its derivative doesn't exist at a point of discontinuity, and therefore it has to have no derivative at that point either. And if you think about the second example that I did, it's a little bit messy down here, but if you look at this, again, we don't really know what the slope is at C2. If you look over here, it looks like the slope is going to be about that. If you look over here, it looks like the slope is about that. You're getting two different values for the slope at the point of discontinuity. That's not actually the reason why a function is discontinuous. I could have drawn this in such a way that it would have the same slope on both sides. We just say the function is not differentiable if it's not at a point where it's not continuous. So that just settles the matter. If it's not continuous, the function has a critical number at that point, and that's that. Okay. So all right. So going back to this next slide. So what does this mean? Local mins and maxes can occur only critical numbers. So think about this. I draw this function here. Next attempt. So take a look at where the mins and maxes actually appear to be. we note here we have, that's a local max. Clearly it's the top of the mountain someplace. Here we have a local min. And here we have a local max. That third one is probably the hardest to appreciate, but if you really consider what the definition is, let me just put in the numbers. Here's C1, C2, and C3. Recall that I said that a local max is the highest value in some open interval around the point. So clearly I can draw those red lines there, and clearly that the local max that I've indicated at the top of that broken function is in fact the highest y value is the highest y value the function achieves in that interval. So that does achieve that does meet the definition of a local max. The point is, if you look at the characteristics of all of these points here, I have f prime of C1 is equal to 0 because clearly the tangent line has a slope of 0. Here, I have f prime of C2 does not exist because the function has a corner. And here, for the reason we were just discussing, f prime of C3 does not exist because the function is not continuous there, so it has no derivative. And these are, in fact, the kinds of places you'd be looking for to find the local mins and maxes. So this is what Fermat's theorem is saying, is that the function, what Fermat's theorem is saying is that the local mins and maxes will only occur at critical numbers. So we can actually find all the local mins and maxes just by finding the critical numbers, the places where the derivative is either 0 or doesn't exist. And then looking at, there are other features we can look at. We'll cover a little bit later how we would identify a min or max if we don't have the graph. But the point is that those are the only points that we have to look at. And there's a certain appeal to this. If you look at point C1, look what's going on. The function has a derivative of 0 precisely because it's turning around. It's going up, up on one side. Then it flattens out and then turns around and starts going down. That's what makes it a maximum. Same thing here in the case of the function not having a derivative at C2. It's just the case where the derivative doesn't exist, that's sort of more anomalous. There are more different things that could happen at that point. So, okay. Let's see. All right, so anyone have any questions or comments, concerns about Fermat's theorem? Oh, good. Getting a few comments. Oh, Fermat. F-E-R-M-A-T. It's French, actually. A lot of people say French. Sorry, say Fermat, but that's like an extreme anglicization of the concept. By the way, one of my famous digressions here. Fermat and I have a bit in common, I guess, although I probably shouldn't say that because he's one of the most famous mathematicians of all time. Fermat is actually known more, he contributed a lot of results to calculus, but he's actually known more for his work on this subject, a to the n plus b to the n equals c to the n, has no solutions has no integer solutions, rather, for n greater than 2. Many of you will recognize that a squared plus b squared equals c squared has plenty of solutions, the Pythagorean triples, 3 squared plus 4 squared equals 5 squared, etc. But it turns out, by the way, this is not calculus. You don't have to write this down, and I will answer the calculus questions in a minute. This is just sort of a fascinating story. Fermat claimed that you can't do something like a cubed plus b cubed equals c cubed and find integers a, b, and c that satisfy it. And he said that's true all the way up to, a 1,000 plus b 1,000 plus c, equals c 1,000, c to the 1,000. So this equation, as soon as you raise the exponent above 2, there are no integer solutions to this. And this was called Fermat's last theorem. Why did he call it that? Basically, because Fermat was actually a mathematical hobbyist. He was not a professional mathematician. This is why I say he has something in common with me. First of all, his name was Pierre de Fermat. Pierre is, of course, the French version of the name Peter, which is my name. It's also the case that I did not used to be a math teacher or any sort of mathematician. Fermat was actually lived about 300 years ago, was a French lawyer and judge. And what some of you may or may not know about me is that before I became a math professor, I was also a lawyer. So we have that in common. Anyway, the reason that this result was called Fermat's last theorem is that because he was a hobbyist in this field, he wrote, he used to just write notes in the margins of his books. And he said, I have a marvelous proof of this proposition, but the margin here is too small to contain it. And then right after that, he died. So it was, in fact, literally his last theorem. The mathematical world then spent the next 300 years trying to reconstruct the proof that he had. The problem went unsolved. It was unsolved at the time I started college, but about 4 years after I graduated from college, I saw my own math professor was on the front page of every newspaper in the world because he had proved Fermat's last theorem. So that was a big event in the early 1990s. Fermat's last theorem was proved by Professor Andrew Wiles. So anyway, I digress. That's who Fermat is. And this is the theorem that we're actually using is Fermat's last theorem. Sorry, I mean Fermat's theorem on the location of extrema. All right, so I get back to the questions. So Ryan asks, would f of C3 be a local minimum if the white and black circles were switched? Would it be a local minimum? The answer is yes, that is true. Actually, would that be the case? No, I'm sorry. It would actually not be a local minimum. If you switch the white and black circles, the problem is that the question is what would happen if at C3 I had made this circle the dark one and this one the white one. What would happen at that point is that C3 would certainly be lower than anything to its right, but it would be higher than anything to its left. So I wouldn't be able to draw this two-sided open interval around C3 and still say that it's the lowest value. In other words, if I had, let's say, something that looked like this, then the question is that C3? And the answer is no, because here, this is clearly higher than anything to its left, but it's lower than anything to its right. So that would not work. So anyway, that's the answer. Okay. Go on to this next result. The extreme values on a closed interval. So we've seen that for a function that is in fact continuous on a closed interval, it does have mins and maxes. So the question arises of where are those absolute mins and maxes? Well, the answer is either it's going to be a local minimum, one that occurs at a critical number, or it's going to be at one of the endpoints. So we'll see that in a minute. Let's see. Sorry, I'm just reading the questions. Function is split into two lines just then. Oh, the question is, the function has, sorry, Amanda asks, does the function have does it have only one local min or max, or can it have multiple ones? And is there any significance to whether it's split into I assume you mean broken, that it's a non-continuous function. The answer is a function can have any number of local mins and local maxes. It goes strictly by the definition. Any critical number is potentially a local min or max, and in many cases they are. So you could have many of them. Just as a very simple example of a function that has multiple mins and maxes, consider the sine function here. We know that these are all going to be local mins and maxes. They also all both happen to be absolute mins and maxes, but there's no limit to how many local mins and maxes a function can have. You can only have one absolute min and one absolute max, although that the absolute minimum value may occur at multiple points, just as you see here. The absolute min of the sine function is -1, and it occurs an infinite number of times. But it's also the case that each of these is, in fact, a local min. Okay. So let's see. I wanted to check something. I'm seeing a up arrow symbol from Eric. I'm just trying to see if to try and get my attention in some way. Sorry, this part is still a little new to all of us. Oh, okay, I see. Got it. Okay. So why does f have to be continuous on a closed interval at all? Why is that the condition for it having for the function having a min and max? I invite you to consider the following functions. I'll draw a few of these. So let's suppose I have a function that looks like this. So here we have f is not continuous on AB, and it has no min or max. Just ponder that for a minute, because I think that some of you are going to look at this and say, isn't that a max? And isn't that a min? But the answer is that they're not, because if you notice, the function never actually gets to these points. They have the open circles around them, so it never arrives there. Here we have, is if we say this is the value 1, we get 0.9, 0.99, 0.999, 0.999. We can put a million nines there. We keep getting closer and closer to 1, but 1 is not actually the maximum value of the function, because the function never equals 1 in this scenario. And make the same argument about the minimum value that I've shown. It never actually gets down to this point, so that's not the minimum value. There are names for these. Which are called. This would be called. You've probably seen this in pre-calc or algebra. This would be called the least upper bound, not bond, bound. Or in Latin, we say supremum, and this one here is the greatest lower bound. And in Latin, we say infimum. So the point is that it never actually achieves these values. It's not that they don't have any significance. It's just that they're not the maximum and min. So because the function has to actually attain those values. So question, wouldn't whatever is just below 1 be the maximum? Well, that's the point, really. And this is the thing that's really slippery about how real numbers work. There is nothing that's just below 1, because no matter what number I give, in other words, there's no way to say what number is just below 1, because as soon as you think you have it, 99999, isn't that just the number that's below 1? What about 9999999? That's a little bit closer. In other words, I can just do that forever. So there is no number that's just below 1, and that's sort of the weird thing about how real numbers work. There's always, between any two real numbers, the 1 and the thing below it, there's always another real number. You just have to just add another decimal point. So are they still critical points? And the answer, of course, is yes. In this drawing, they are, because the function is not continuous at those points, and therefore it's not differentiable at those points, so the derivative doesn't exist. So yes, this is certainly C1. And by the way, just to be clear, it's actually the x values that are the critical points, not the points themselves. Okay. So yes, they are critical. I'm just trying to demonstrate why it is that you need the conditions continuous and closed in order to guarantee that these exist. So let's consider another example. So here, the interval's not, what we have is the interval is not closed. And as you can see, there's no min or max. On the left side of this interval, I would say the interval here, I would define it as 0, infinity, like that, which is not a closed interval. As you can see, here the function goes up forever to positive infinity. And on this side, it approaches 0, but it never actually gets there. And this is, I think, Eric's earlier question about could an asymptote be a min or a max? Answer is it could be, depending on the shape of the graph, but it's certainly not guaranteed to be, because for the same reasons I was discussing in the diagram on the left here, the 0 is a value that this function never attains. You can sort of imagine this as being the function y equals 1 over x. It never gets to 0, so 0 is not a max. It's just really it's really just a greatest lower bound. So okay, do a third example. So here we have f is defined on AB, like that. So it's not defined on a closed interval because it's a half open interval. And by the way, a half interval is neither open nor closed. It's just called half open. So we'd say the interval is not closed. But sorry, f has both min and max. So what's actually going on here? Because clearly this is a min and clearly that's a max. Well, what am I talking about? The point here is that a function can have a min or a max on an interval that doesn't meet these requirements, but the requirements of continuous on a closed and bounded interval. It's just that, just like with the intermediate value theorem, how it might be the case that the function had some solution, the question is, what does the theorem say it? We saw that with the squeeze theorem also. If the hypotheses of the theorem are not satisfied, the theorem doesn't apply. That doesn't mean the statement is false. It just means we don't know anything from the theorem. So this is an example of a function that does have a min or max, even though it doesn't meet the requirements of the theorem. So you could have a min or max, you just don't know from the theorem. The only guarantee is that if the function is continuous on a closed or bounded interval, it will have a min or max, and those mins and maxes will occur at either a critical point or an endpoint. Consequence of that is that we only have to find the critical points and endpoints in order to find the mins and maxes. So that takes me to this process, which is called optimization. It's how do you find the extrema of a function on a closed interval? Answer is first, find all the critical numbers. In order to do that, you find the derivative of the function, you set the derivative equal to 0 and solve the equation. And then you look at the places, also look for the places where the derivative is undefined. As we've seen, that gives you your critical numbers. Next, you evaluate f at all critical numbers and at the endpoints of the interval. I will tell you what the most common mistake I see is in solving this, which in using this process, which is that people plug the endpoints and the critical numbers back into the derivative, into f prime. That's not what you're interested in. What you're interested in is the maximum value or the minimum value of the original function, not of its derivative. So what you do is you take the critical numbers that you found through the derivative, but you plug them back into the original function. 3 is once you've found all those those y values, you simply look at which ones are the highest and which ones are the lowest. And based on this combination of theorems, we know that we've found the highest and lowest values. We found the absolute extrema of the function. So just to put things in perspective, I do think this is a remarkable process, and it's actually one of the most important things that you're going to learn in calculus. It's one of the most important applications of calculus, is how do you find the highest and lowest values of something. If you think about it, every interval contains infinitely many numbers. We can't check them all, but what this allows us to do is boil the process down to a very small number of them. We just look at only the endpoints, of which there are only 2, and then we look only at the critical points, the critical numbers, of which there are going to be a small number. Those are the only points we have to check to guarantee that we found the highest and lowest values of the function, even if it's some horrendous function that we can't graph. Everything I've done, you've seen the picture of it, but this process works even if you can't graph the function. The applications of this are very, very important, because anything that you can define as a function, any process, whether we're talking, about what the best way to the best way to manufacture plastics is, we're to make it more timely, what's the best number of people to keep apart from each other to keep a virus from spreading. Any of these things, as long as you can write a function that describes the process, you can simply run it through this optimization process and find the best the best way of doing it. Of course, the complicated part is finding the correct function, which has to be done experimentally, and that's what science is all about. But this is how calculus is actually used in the service of science. So before we get to the word problems, really, which come really at the end of the chapter, I'm just going to solve the problem of how do you find the extreme values of a particular function. So when I say extrema, I mean extreme values. Let's find the extrema of f of x equals 2x cubed minus 15x squared plus 24x plus 7 on the interval 0, 6. So we do, in fact, have a closed and bounded interval, and we do have a function that's continuous on that interval. We know this function is continuous because it's a polynomial, and we've already covered that polynomials are continuous wherever they're defined, and they're defined every place. We know the interval 0 to 6 is closed and bounded. So first, let's find critical numbers of f. So we have f prime of x. We're going to just find the derivative of this function. So that's going to be 6x squared minus 30x plus 24. And of course, that 7 has a derivative of 0. So in order to find the zeros of that, we want to find the places where that's 0. So as we all know, what we want to do is factor it. So this is going to be 6x squared minus 5x plus 4 which equals 6, x minus 4, x minus 1. So f prime of x equals 0 implies that x equals 1 or 4. So 1 and 4 are critical numbers. There are no points where f prime does not exist. There aren't any such points because the derivative is still a polynomial, and polynomials are, of course, defined everywhere, so that we don't have to worry about any points where the derivative doesn't exist. Okay. Next part of the process, we evaluate f not f prime, but f at critical numbers and endpoints. So what I do is the endpoints are, we know that the critical numbers are 1 and 4. So f of 1, call that, I'm plugging it back into the original function f. I've done the calculation already. So f of 1 equals 18. So that's critical number. F of 4 equals -9. I'm just cataloging here why I'm evaluating at these points, because 1 and 4 are critical numbers, but then we also have to do the endpoints because we know the min and max might occur at an endpoint. So f of 0 is equal to 7, and f of 6 equal to 43. So that's the endpoint of the interval, and that's the other endpoint of the interval. So now all we have to do is look at which ones are the highest and lowest values. Here, that's the minimum value, and that's the maximum value. So now we answer the question. The absolute min is -9. Absolute max is 43. And if you notice, I can be absolutely confident that I have actually found the absolute mins and maxes, even without checking any other points and without graphing the function. Now, why is that? Why do I only have to check these points? It's a comprehension check. You can post a chat on that. No one. Yeah, because it's a closed interval. And yeah, Zach got it right, because extremes only occur at these types of points. So they're the only ones I have to check. I haven't drawn the graph of this function at all, and yet I can be absolutely confident that this is the correct answer to the question. So, all right, so that's how optimization works. By the way, I just want to say something about the numbers 4 and 6. These are the locations of mins and maxes, not mins and maxes. A lot of people say, oh, I found, if you notice here, I found f of 4 equals -9. I get a lot of answers that say, oh, 4 is the minimum. No, 4 is the place where the minimum occurs. The minimum value is still the y value. In other words, the value we get from evaluating f. Okay. All right, so any questions about this process? I've actually solved and posted, we'll post with the notes, a couple of other more complicated examples of this that you can read, but I would want to move on the last couple of minutes to the last topic that we'll do. Just wait for the question. Well, no, because I would. So the question is, would you be able to put f of 4 and f of 6 as the answer? And the answer is no. You'd have to actually find. You'd have to find the values. You would have to actually evaluate f of 4 and f of 6. I mean, I would certainly give you credit for recognizing, that the min and max are y values and not x values. But to get, full credit, you'd have to actually find the numbers. Okay. So I'm going to skip over the other examples because I want to get to the last topic, but I will post those in the notes. If I have time, I'll also even make a video demonstrating them that you can watch offline. So the last result, and we're still in section 4.2, the last result is something called Rolle's theorem, or sometimes called Rolle's lemma. If you're wondering what a lemma even is, a lemma is a theorem. It's just kind of like a mini theorem that you use really to prove a theorem that's more interesting. Historically, actually, Rolle's theorem came first, so it usually gets its own name as a theorem, but you sometimes see it written as Rolle's lemma. So Rolle's theorem says is, assume that f is continuous on the closed interval AB and differentiable on the interior of that interval, the open interval AB. If f of A equals f of B, then there exists at least one number C in the interval, in the open interval, such that f prime of C equals 0. Now, why is that? Let's suppose that I have, here's A and B. So here we have f of A is equal to f of B. In other words, they start and end at the same y value. So what Rolle's theorem guarantees is that there must be at least one point in the interval where the function flattens out. So here we have C1 and C2. So here we have f prime of C1 equals 0. You can clearly see that because the tangent line is horizontal. And here we have f prime of C2 is also equal to 0. So what Rolle's theorem does is it guarantees that if these conditions are true, then there will be at least one point. There may be more. I've shown you that there's actually more than one point, but at the very least, there's going to be one point where the function has a derivative of 0. Perhaps a simpler example might look like this, like if that's A and that's B, here we have this, there's only going to be one point C, but we have f of C equals 0. So there will be at least one such point. I don't want to go through the proof of this, but let me just give you a counterexample just so you can sort of understand why these conditions have to be the case. So function certainly has to be continuous on the closed interval. So let's do a not continuous function. So let's suppose that I have, that's A and that's B. So here, so here's an example of a function where it's not continuous on the interval AB, and even though FA and FB are the same, there's clearly no point where the function flattens out. Its derivative is always going to be positive because it's just two lines of positive slope. Similarly, if I had something like this, like where that's A and that's B, Here the function is continuous. Here I'll mark this as not continuous. Here it's not differentiable on the entire interval. And we can see that here we have m equals 1, and then here we have m equals -1. The function turns around, fa and fb are equal to each other, but the function never actually has a derivative of 0. So you have to have these conditions. The function is continuous on the closed interval and that it's differentiable at least on the interior of that interval. So what sort of question are you likely to encounter on this? I'll do this just in the last couple of minutes. So let's verify that Rolle's theorem is satisfied for f of x equals sine x on the interval pi over 4 and 3 pi over 4, and find the number c whose existence is guaranteed by Rolle's theorem. So 1, f is certainly continuous on pi over 4 and 3 pi over 4, and differentiable on pi over 4 and 3 pi over 4. Note that I'm switching that to round brackets. This one should be, just to be clear, those are square, they're round in the second case. We know this is true because we know that the sine function is continuous and differentiable every place. We've already covered that. So, all right, so it's continuous and differentiable. And so now what we can do is, so we know the conditions of Rolle's theorem are satisfied. So that verifies that Rolle's theorem does apply. Now what we're going to do is we're going to find the number c. So we know that f prime of x is equal to cosine of x. What we want to do is solve cosine of x equals 0. Well, where does that occur? Cosine of x equals 0, since that's the cosine function. Pi over 2, 3 pi over 2, 5 pi over 2, etc. So that means that x equals pi over 2 plus pi n for all integers n. But of course, we're really only concerned about the one that's inside the interval. So we know is that pi over 2 is the value where cosine x equals 0 inside the interval pi over 4, 3 pi over 4, because we know that if I have here, pi over 4, 3 pi over 4, I know that pi over 2 occurs right there. So that in fact does show that c is equal to pi over 2. And we know this to be the case because if you actually look at the sine function looks like this. And you know that if that's pi over 4 and that's 3 pi over 4, we can see that in fact sine of pi over 4 equals sine 3 pi over 4, and right in the middle there is in fact a horizontal tangent. Okay. Anyway, I guess we're out of time. So that's it. Any last comments before we break? Oh, what would n be? That just refers to the idea that it could be any integer. It could be 1, 2, 3, -1, -2, -3. I will say happy birthday to you, but I will not sing it because I do not want to break the glass on anyone's computer. As to those of you saying thank you, you're welcome. How soon will the recording be posted? I think the Big Blue Button does it in about half an hour or an hour, and then sometime in the next few days, I'll put it up on YouTube as well. Okay, well, I'm glad that everybody enjoyed this. I really do hope. I think that actually having this sort of connection is going to be important in the next couple of weeks. So I really look forward to seeing you all in class. Thank you for coming, everyone. I will see you on Thursday. Have a good workshop with Roger tomorrow. Leah, I will take a look at that. I may have made a mistake, but I thought that I will address that. Don't worry about it. Okay.